Right, so welcome everyone. So good morning, good afternoon, or good evening, depending on which part of the world you are. And welcome back to this UK Quantum Fluids Network webinar series. My name is Davide Proman, and I'm very happy to chair this session. Today we've got Giuseppe Baio from University of East Anglia. Giuseppe studied physics in Italy at Palermo University, and then he moved to Strathclyde to do a PhD, and is now in his first postdoc after his PhD. He joined University of East Anglia a couple of years ago, if I remember well. And so today he's going to talk about monopoles, Alice rings, and topological interfaces in spinor BECs. So Giuseppe, please.
Well, thank you very much, Davide, for the kind introduction. And so I'm a postdoc at the University of East Anglia, and it's really a pleasure for me to share my research here with you. I've followed many of the talks within the Quantum Fluids Network, and I have to say this is a really vibrant community, so I'm really happy to do that here. So this is going to be mixing some results about topological excitations in spinor BECs, especially monopoles, closely related concept of Alice rings, and later on I will discuss topological interfaces that we can realize in this system. So I want to start by introducing the concept of spinor BECs as basically a Bose-Einstein condensate when the optical trapping is such that we retain the internal or magnetic degrees of freedom of the atoms. So we essentially work with hyperfine transitions of alkali atoms. So we've got the manifold of states with, for example, total angular momentum equals 1 or 2, and that means essentially we have a vectorial order parameter. So we go from a situation where the scalar order parameter is just a complex number with amplitude and phase, and then we start to introduce this vectorial wave function with this spinor part, which is going to be three-dimensional in the case of spin 1 condensate, where f equals 1, or even five-dimensional in the case of f equals 2. And this is interesting. This is an interesting set for topological excitation, because we start to have phenomena like the mass circulation that depends not just on the superfluid phase, but on the orientation of the spinor as well. So our framework is that of the mean field theory, and the system is basically described by a mean field energy functional, or Gross-Pitayevsky energy functional, where we basically have something like the competition of two interaction terms, which are spin-independent and spin-dependent interactions. And so this, for example, this depends on the magnitude of the spin, and this object has a symmetry of it's basically the gauge angle, which is the U1, and spin rotation is symmetric via the action of these symmetry groups. That means that spinors are related to each other via transformation like this that we parameterize in terms of the gauge angle and three Euler angles. So this competition leads to, for example, in the case of f equals 1, two magnetic phases, which are the ferromagnetic phase here on in the left, which we represent with spherical harmonics, and where the spin is maximal, and we see that essentially the effect of phase rotation is the same of spin rotation in this case. So that means that the order parameter is essentially that of spin rotation only. And we also have a polar phase where the spin vanishes, and we have this continuous rotational symmetry around this axis, and a Z2 symmetry that couples both the gauge and the spin. And we can introduce external fields in the picture that enters this energy functional via the linear and quadratic Zeeman shifts. And these start to introduce second order phase transitions, as we see here from this phase diagram as a function of P and Q. And they introduce basically ground state that interpolate between these two phases. So for example, here we have this antiferromagnetic phase where the interpolating parameter basically depends on the linear shift, and it's able to interpolate between the two states. So, as I said, this is this system exhibits a rich phenomenology of topological excitations, which rigorously are mathematically characterized by so-called homotopy groups, or associated to each order parameter manifold. And we distinguish here between the first homotopy group, which basically describes line defects. And this could be vortices like phase vortices or spin vortices, but also a combination of the two, such as in the case of half quantum vortices or fractional vortices in general. But we can also have higher order homotopy groups that describe excitations which can be both non-singular, like in the case of 2D skyrmions, or point defects, such as in the case of monopoles, and we are going to focus on those during the talk. And in the even higher order cases, we can have non-singular textures in the form of topologically stable solitons, such as 3D skyrmions of even knotted structures. So in the spin 2 case, we essentially have the appearance of a further interaction channel between atoms, which in the mean field limit, it essentially is proportional to this quantity here, A2 which we interpret as the formation amplitude of pairs of atoms in a spin singlet state. And this make things a bit more complex, but essentially the idea is that we have a higher number of phases appearing in the system. So we have the two ferromagnetic phases depending on the value of the spin. So we have the ferromagnetic 2 phase, which is this donut shape, and the ferromagnetic 1, which is this hourglass shape in the spherical harmonics. But we also have non-magnetic phases, and these start to have discrete symmetries, such as in the case of this cyclic state, where we have a tetrahedral symmetry which combines both spin rotations and the action of the gauge transformation. And we've got two nematic phases, the uniaxial-nematic and the biaxial-nematic, which are energetically degenerate in the mean field limit without Zeeman shifts, and but nevertheless they are topologically different. So we have a situations like this, a phase diagram depending now on the two interatomic interactions. And when we start to introduce the Zeeman shifts, we also start to see second order phase transitions in this diagram, and it also we also break the degeneracy of the nematic phases, and we in favor of one of the two. So what we are going to do here is we look at basically how the relaxation and the dynamics of excitations like monopoles works in a system like the spin 2 BEC. So this is going to be the first part of the talk, where I will introduce the concept of the Alice ring, and then I will show how a related object that is called spin Alice ring arises from the relaxation of a monopole in the uniaxial-nematic phase of a spin 2 BC, and then we are going to look at the relaxation of monopole textures in the other phases of the BC. And in the second part of the talk, I'm going to look at topological interfaces and all of the defects that can cross these interfaces between the various magnetic phases of the spin-2 BC. And finally, if there's some time left, I will discuss a bit the experimental realization and possible further direction arising from this. So first of all, another essential concept is that of an Alice ring, and this is essentially a ring defect that was introduced for the first time as a relaxation, an energy relaxation channel for the decay of toothed Polyakov monopoles in the context of high energy physics, essentially. And but it's also found in liquid crystal in the decay of a point defect in a nematic liquid crystal. And in the context of BCs, it was discussed in the case of a spin-1 BC in the polar phase, where the monopole essentially is formed by a radial orientation of the polar order parameter, such as in this case, which gives a point defect where the density, the atomic density is depleted at this singular point. This is, of course, very energetically costly, and what the system does to reduce its energy, it develops a deformation of the order parameter, which is such that in the asymptotic limit, the monopole configuration is left unchanged, but in the vicinity of the singularity, basically the singular points shift from the point defects to basically a disclination loop or disclination ring. And we can also see that by plotting the component densities, which show that there is a spatial separation of the singularity, of the singular lines, which means that in this case, the core of the Alice ring is ferromagnetic in the spin-1 BC. Also, another important property is that of is a topological property, which is essentially the fact that when there is another monopole interacting with an Alice ring, in essentially it rotates around the ring, but it's also valid for a line defect with a disclination. But what happens is essentially it turns into an anti-monopole after one rotation, and this may seem as a pretty abstract property, but it serves us as a guiding principle in establishing whether a certain excitation is an Alice ring or not. And finally, just to complete the picture, Alice rings were recently observed experimentally by the Amherst group, I think 20 years after the first prediction. And this gives a nice complete picture regarding the spin-1 BC. So we are going to look at the spin-2 case, and the phase that we are going to be focusing first is the uniaxial-nematic phase, where essentially this is the only phase that supports isolated point effects in this system, which means that the second homotopy group of the order parameter manifold is non-trivial. And the monopole in this phase are constructed by a radial orientation of, in this case, the nematic axis. So we can associate to these objects a proper monopole charge, which is defined in this form, this surface integral. And in this case, we have that the nematic axis is unoriented, and therefore it only matters the modulus of this number, because it basically means that a monopole is equivalent to its anti-monopole. So in the spin 2 case, we explored the energy relaxation by integrating the Gross-Pitesky equations in imaginary time. And we do that by to single out the role of energy decay. And what's different in this case is that we've got different phases that can feel the singular, that can feel the defect core. And what we observe is essentially a ring defect, which is now which has now a pi disclination of the nematic axis, as we see from this spherical harmonic representation. But also we notice that there is no mass circulation when we wind around the ring defect. And that is because in the uniaxial-nematic phase in spin 2, we've got that the Z2 symmetry couples to the spinor part only. So disclination can occur without any mass circulation. And that is why we use the name spin Alice ring in this case. And the other interesting consideration is about the structure, that the local structure that this Alice ring has, because when we looked at in detail, we see that there is essentially a region of biaxial-nematic order parameter arises around the core of the ring. And this means that we have different topologies at different scales as a function of the distance from the defect core, and therefore we use this terminology of a composite core structure that we can also locally parameterize analytically by means of this superposition form, where we can essentially go from the uniaxial-nematic state, and we have a half quantum vortex, which is this ring here that you see at a certain radial distance, and then it goes to the disclination, to the pi disclination of the nematic axis in the outer part. And also, I mean, to distinguish between the two nematic phases, we introduced this A3 knot, which is essentially the formation of trios of atoms in a singlet state. And this gives a way to visualize this alternance between the uniaxial and the biaxial-nematic phases. And also, if we propagate the Gross-Pitesky equations in real time, we start to see the onset of. Actually, we do that in complex time to introduce some dissipation in the system, but we start to see the onset of oscillations in the system, and we can see that in this movie. So we have essentially here on the left the spin magnitude. So we start from the spin Alice ring configuration, where we don't have any ferromagnetic state arising, and then we start to see essentially the some ferromagnetic rings that arise in the system, then drift away from each other, and then they annihilate at some point, and they come back with opposite circulation, and then they overlap again to form the spin Alice ring, the initial configuration of the spin Alice ring. So this is basically an oscillation cycle that repeats in this system. So what we did to unpack the vortex structure of what's going on in these oscillations, we introduced the vorticity fields, which have this form, essentially the curl of a current vector, which in this case is the mass current where we only have one index, but it can also have we can also have the spin vorticity associated to each spatial component of the spin. So we can single out four different instances of this oscillation cycle, and we see that, for example, if we plot here the Z component of the mass circulation, we see that there is a non-zero mass circulation in correspondence of the ferromagnetic regions. And when we plot this scalar quantity, which is essentially all possible, the spin circulation for all possible spin component, we see that these ferromagnetic rings possess an individual vortex structure. But and also, if we follow the spherical harmonics around these rings, there is we see that the circulation is the same of a half quantum vortex. Then these drifts, as these rings, as they drift away from each other, they end up in this what we call a split core configuration, which is essentially is two points, density depleted points joined by a disclination segment. And we see now the rings emerging with opposite circulation and then re-overlapping again in a single ring with spin circulation only, which is the spinalis ring. And this is a bit expanded in form because of the presence of dissipation in the system. Nevertheless, these half quantum vortex rings, they're not to be understood as individual vortex charges, because if you wind, we see that the transition is mediated by the presence of, in this case, a biaxial or cyclic state. So they are part of an extended vortex core region. And so in the other phases of the condensate, we have that the second homotopy group is trivial, but and this means that there are no isolated point defects. But we can find monopole textures which are attached to some line defects. And the most well-known example is that of a Dirac monopole found in the ferromagnetic phase, where we essentially have a more complex spin rotation that it gives a point defect attached to a singular line, which is called Dirac string. And in the ferromagnetic phase, we can essentially define an effective vector potential, which is such that the associated magnetic fields is exactly the same as the original construction of Dirac. And what we did here is to generalize this construction to the other non-magnetic phases in spin 2, because we want to look at at the role of the discrete symmetries of these phases in the system, and in particular of the biaxial-nematic and of the cyclic phase. So in the first case, the state that we construct is essentially a monopole which is skewered or is penetrated by a spin vortex line. And we see that energy relaxation in this case, in the biaxial-nematic case, leads to a spinalis ring, once again, but it's now a spinalis ring that encircles the spin vortex line. And we also see the onset of dynamical oscillations, as we saw before, for the uniaxial-nematic case, which leads to the split core configuration and the ferromagnetic rings, and which they eventually overlap again, forming a single ring of spin circulation, which is the initial spinalis ring. While in the cyclic case, we analyze the energy relaxation of both configuration, that is the axially symmetric configuration where we have the monopole penetrated by the spin vortex line, and the case where the spin vortex line extends in one direction only. And we start to see some differences, and in particular, in the first case, we don't have the formation of a spinalis ring, but we see this formation of ferromagnetic rings directly from energy relaxation. And the interesting thing about those is that they exhibit fractional circulation in units of 2/3 of pi. And in the other case, we see that we found a core that is not axially symmetric because of essentially the symmetry of the cyclic order parameter. And this is also seen by the appearance of 4 individual ferromagnetic regions within the core. So this ends our results about monopoles. And I'm going to go to the second part of the talk, where, as I said, I'm going to introduce the concept of topological interface as basically the physical boundary within a system where we have different symmetries in different regions. This is a situation that is often found in the physics of the early universe, in the theories of the early universe. A series of successive phase transitions can lead to so-called hybrid defects, such as, for example, monopoles, which are joined by a singular line, or domain walls, which are joined by closed defect lines. But it's also a situation found in superfluidity. That's the other paradigmatic example, where we basically have defects that can penetrate the phase interface between the so-called AB phases of helium-3. And these are found in the shear flow of between these two phases. And but they can also arise from a simulated brain annihilation process. And the defects that we find here are called bujums, but essentially are point defects that exist at these interfaces. And the basic concept here is that defects cannot cross a topological interface unchanged, but they need to evolve somehow to another defect, or they must terminate at the interface. So the case that was in the context of spinor BECs, the case that was discussed mostly so far was the spin 1 case, where we can have phase or spin vortices that penetrate the polar to ferromagnetic boundary, or we can have a defect line that joins a non-singular texture, or it can terminate into a monopole in both the phases. And as we saw before, at the concept of the basis of the concept of interface, there is this interpolating states which arise when we have Zeeman shifts in the system. And in this case, in the polar to ferromagnetic boundary, we have that this situation can be realized by means of the linear Zeeman shift. So we are going to go to the spin 2 case. That is essentially where we have a higher dimensional spin, and we start to see the effect of discrete symmetries and potentially non-abelian physics in this system. So the first situation I want to focus on is the interface between the two nematic phases, namely the uniaxial and biaxial nematic. And this is realized if we consider this one parameter family of three component spinors. And we've got this eta here, which is the interpolating parameter between the two phases, and we also have these phases that we manipulate individually in order to create all possible vortices. And we see that already in this case there is a complex phase interplay, and this can be seen by plotting the two relevant quantities, which are the pair formation amplitude and the trio formation amplitude of spin singlets. And by plotting those as a function of the parameters, we see that, for example, in this case, where the relevant phase difference amounts to 0, we have transition between the biaxial and uniaxial nematics, which is here at the bottom, which are in particular in blue, we have the biaxial, and in green, the uniaxial, according to this color map. But we can also have transitions all the way to the cyclic when this A3 naught is maximal. Depending on the value of the phases. So when we look at the mean field energy in the uniform case, we see that, for example, in the case where the spin singlet interaction is negative, the minimum is attained in the boundary of this space, which means that we can have transition, we can stabilize transition between the uniaxial and biaxial nematic phase. So, for example, if we start from this point where we have a perfect coexistence of uniaxial and biaxial, we can end up stabilizing the two phases in different regions of the condensate by simply varying the quadratic Zeeman shift between two opposite values. And then once we have the spinor that describes the interface, we realize we can obtain all of the defects by simply winding the phases, or via spin rotations, like we did before in the case of the monopole. So the first example I want to show is that of a phase vortex, which we numerically investigate by means of integrating the Gross-Pitayevsky equations. And this is just this is constructed by simply winding the global phase, and we have a situation like this depicted in this cartoon, where what we observe essentially is the onset of a dynamically unstable mode that is located roughly at the interface between the two phases. And what this causes is the separation of the vortex lines. So we end up with a situation where the vortices in each phase are filled with the other phase. And interestingly, these vortex cores are not axially symmetric, and we see that due to the presence of these cyclic regions here that arise in these vortex cores. And also the presence of these alternance of phases, namely biaxial, uniaxial, and cyclic, is such that we can find these vortex cores are a source of topological interfaces around the singularity. So we find interfaces around the vortex core themselves. The other example in this interface is what we call Bujum, which is essentially a point defect join attached to a spin vortex that in this case is a monopole in the uniaxial-nematic phase here at the top, and we've got the spin vortex line in the biaxial-nematic side of the condensate, and we see that energy relaxation here once again favors the formation of a spin-Alice ring, but it's now embedded within this larger uniaxial-biaxial manifold, and it's locked at the interface. But we can also, by playing with spin rotation, we can also analytically construct the opposite situation. That is where essentially we hide the singularity in the other part of the condensate. So we now have a non-singular monopole textures in the biaxial-nematic and the singularity in the uniaxial part, and we once again find a spin-Alice ring, but it now has a different orientation, and it's also locked by the core of the spin vortex in the uniaxial-nematic side. And so, as I said before, the other interesting interface that we find within this family is when this relevant phase difference amounts to pi. That means that we move along this line, essentially, and we now have a situation where in the case where the spin singlet interaction is positive, we have a continuously interpolating ground state between the two nematic states and the cyclic, which arises when the quadratic Zeeman shift vanishes. So in particular, if we consider only the transition between cyclic and biaxial-nematic, this is an interesting setting for all possible spin rotations in the system. And in particular, that depends on which axis we choose. So we can construct, for example, spin half quantum vortices connecting through the interface, or integer spin vortices. And interestingly, these different vortex classes end up developing very different cores, such as, for example, in the spin half quantum vortex here on the left, we see that there is this uniaxial-nematic core penetrating the cyclic-to-biaxial-nematic interface. But in the other case of the integer spin vortex obtained by rotation around another axis, we have again a uniaxial-nematic core, but it's now tilted, and the transition to the outer layer occurs via a ferromagnetic state. And what's also interesting is that these cores arise in the presence of the interface only in the system. That means that the dynamics of this object is strongly influenced by that. So finally, the last two interfaces I want to show are when we have transition to the ferromagnetic phases, and this can occur from the cyclic state within these two component families of spinor, or in this other one where we have instead the biaxial-nematic case. And in this case, we can individually address the phases in order to construct vortices which have fractional mass circulation, such as in the cyclic limit. We can have a 1/3 quantum vortex or a 2/3 vortex, depending on how we rotate the cyclic order parameter around this axis. So these two examples, for example, in the cyclic-to-ferromagnetic case, are shown here, where we have this is the in the left we've got the 1/3 case, and we see the emergence of the ferromagnetic phase that is now stable in the core of the 1/3 vortex. And we've got a singly quantized vortex in the ferromagnetic phase at the top. That means that we can have a mass circulation that varies along the vortex line. And in this other case, we have a 2/3 vortex where the stable core is given by the ferromagnetic 2 phase, and this connects to a vortex-free state. And this is interesting because it can also be joined to a coreless vortex, which we can see here with this fountain-like spin texture. And this is interesting because there are protocols available for the construction of coreless vortices in the spin 1 case. And this could be a way, since in this case, this connects to a doubly quantized vortex here at the bottom. So the instability of this object, it could be seen as a way of producing fractional vortex connection experimentally in the system. And the final example I want to leave you with is that of non-abelian vortices, and these are constructed in the biaxial-nematic to ferromagnetic interface. And in particular, the biaxial-nematic is the simple manifold that supports non-abelian defects. And we constructed a pair of non-commuting vortices that in this case terminate at the interface, and they start to develop an interesting cyclic core. So it's also a way to have an interesting cyclic to ferromagnetic transition within the vortex core. And in this case, it could be an interesting setting for non-abelian reconnection, which would occur only in one part of the condensate, or other processes like, for example, swapping, braiding of non-abelian vortices, and so on. So finally, I think I have some time for discussing the experimental realization. This can be done in two ways. We can play with multi-photon transitions. In this case, is a two-photon transition that couple two of the magnetic states, such as in what they do in the Rochester group. Or it can also be done with the help of spatially dependent magnetic field. This is in particular a combination of a quadrupole field and a time-dependent time-dependent homogeneous field that is such that the 0 point of the field can be brought inside the condensate. And this is useful for imprinting monopoles in the BEC. And in the case of the interface, the challenge is that of controlling the Zeeman shifts in a differential way. And we are exploring that with the Amherst group. And finally, once we can also adopt combination of magnetic imprinting and phase conversion. That means we can construct vortices in the F=1 manifold, where we have polar and ferromagnetic phases, and we can convert to those to the spin 2 phases via a series of optical pulses. So that's pretty much it. I hope I have convinced you that the spin 2 BECs is an interesting system for topological excitations such as monopole, but also vortex connections across interfaces. And this results into interesting defects and interesting dynamics, such as we saw for the Alice rings, but also in the case of vortex instabilities in general and non-abelian vortices. So as I said, we are also interested in thinking about techniques for imprinting this object in the spin 2 BC. And we are also exploring other dynamical creation processes for defects, such as in the case of quenches, or even engineering the a reconnection process for non-abelian vortices, and hopefully all of these in the direction of establishing spinor BCs as emulators of topological excitations and interface physics in all of the scenarios where these objects are much less accessible. So that's it. I thank you very much for your attention, and I look forward to some questions.
Thank you, Giuseppe. Thank you for the great talk. Yes, so please feel free to unmute yourself and ask your question, or just raise your hand, and then I will call for your question. Maybe in the meanwhile, I can ask a couple. Well, I've got a couple of questions to ask. Yeah. Maybe I can start with one, and then let's see. So, well, the first question that I have is that it's a general question about various decay mechanisms that you described when you were talking about the stability of some of these many different defects that you can generate. So if I got it right, you said that you were evolving the Gross-Pitayevsky-like equations in imaginary time.
Yes. Yeah.
So I was just curious. I mean, how much, if I were to look at the instability from a dynamical point of view, so really, I mean, using real time and not imaginary time.
Yes.
How much energy would be released from the decay from one structure to the other? And if there is a lot of energy, how this energy would look like? Would be some kind of sound excitation, things like that? Can you?
Yes. Well, of course. I mean, as I said, the reason why we do that. Well, we do that in imaginary time to single out the role of the energy energetic instability. But there are also other phenomena. There are also other phenomena such as the oscillations of the spin-Alice ring, which only occurs in is a dynamical process because it only occurs in the when we integrate in real time. So in the so of course we use complex time to let's say mitigate bad effects that can arise from extremely fast oscillations, but yeah, in general, I would say that there may be some other collective modes which are let's say excited by the decay of those. Yeah.
I see. So when you were talking about the oscillations, these were in real time.
Yes, these ones these are in real time. Yes.
All right. Okay.
With some bit of dissipation, but this is because in imaginary time you only see the expansion of this spin-Alice ring, whereas these phenomena where we have ferromagnetic rings and the split core and this oscillation cycle in general, this is in real time.
See. And so it would be completely periodic?
Yes, that's what simulation seems to show, and it would be interesting to gain some more insight about this mode, this oscillating mode, and Of course, it could be a bit difficult to do that in the ring defect, but we can perhaps say something more when we look at pi disclination. So to see whether these oscillating instabilities are present in a pi disclination. That would be analysis string rather than a ring. That would be a slightly simpler system to analyze.
And well, I also have another question. So it seems to me, if I got it right, that some of these of these excitations are sort of localized excitations.
Yeah.
But like compact in some sense, and then some others are non-localized. So, for example, I have a sort of vortex tube that will continue until the boundary of your system.
Yes.
And so how important would you say that experimentally is to deal maybe with localized or non-localized excitation, and how difficult or important or difficult is to distinguish between them?
Well, of course, I mean, these are different kinds of excitations, and there are different protocols to engineer those. But in general, I would say that let's say the line defects, for example, are slightly easier to imprint in the condensate. While of course in the localized case, such as point defects or even the ones described by higher homotopy groups like skyrmions, or this would need more careful scheme because of the fact that it's a localized excitation.
Are there any questions for Giuseppe? Well, I have another question actually regarding the experiment. So it's it's notoriously is very difficult to observe vortices already in a scalar BEC because of the imaging process, and most of the time the BEC trap is released and the BEC expands, and then it's difficult to observe it. So how easy is to observe vortices in spin BEC? Or is it better actually to observe them in a spin BEC, because you can maybe separate the spin component experimentally?
Well, you can do that, such as I mean, these images you see here. You are imaging the densities of the population of each magnetic levels. So that you can do. It would be slightly more difficult to observe phenomena like the non-axisymmetric cores, or even these spin-Alice ring oscillations. Because in that case, well, if you image the component only, you would need to see separation of the singular lines giving, for example, ferromagnetic states. But this could be slightly more difficult. So it's of course important to find the proper experimental signatures of this phenomena. This is one of the challenges. But I mean, the idea of going to higher spin cases, because of you enable topological processes that only exist in these higher dimensional contexts. Yeah.
Yeah. Thank you. I was thinking about some type of interference, for example, so once you split the two and then you let them interfere to look maybe at some pattern of interference to measure some phase or something. But yeah, I mean, it's
that could be done for detecting phases, right?
Yeah. Right. Well, are there any further question for Giuseppe? No. Okay, so I think that the next webinar is going to be in 2 weeks' time. More information is going to come soon, and yeah, if there are no further questions, let's just thank Giuseppe again, and yeah, we will resume in 2 weeks. Thank you.
Thank you, everybody.